Hey guys, it's IDW, and today we are going to be talking about instruction sets, which is the very last thing before we can really start to work on our CPU. Because basically, when you're building a CPU, you're trying to implement your instruction set. And so, yeah, once you understand the instruction set, you can really fully build a CPU. So everything that we've done up to this point has really led up to this, so yeah, let's just start looking into it. So first of all, I've actually already sort of been over instruction sets, but they're basically like the different workshop designs. One workshop might have different things that another workshop might not have. For instance, two computers that have the same instruction set are actually pretty much the exact same thing, other than a few functional things. One might have a faster clock speed and, yeah, stuff like that. Anyways, so at the same time, this makes it so that some computers might have a lot more functions than others, and so they might have like more tools in this analogy. But others might not have as many tools, but at the same time they have plenty of space for you to put the stuff that you're just not working on right now, or registers. And this is basically what makes instruction sets important. It basically makes each computer unique. So, yeah. Anyways, so there's basically 5 main parts of the instruction set. There's the functions, which are basically a list of the stuff that you can do in a clock cycle. You have some information about the registers, also is pretty simple. Some information about the memory, still pretty simple. Other stuff that's in the control unit, and finally the bit layout, which is not going to be very fun to explain, even though I say it there. Anyways, so functions. Functions are basically what you can do during one clock cycle, and each instruction set comes with a complete list of all of the functions that the CPU is capable of doing, and they're almost always really simple operations. You're not going to be doing like a square root or multiplication and division in one sequence, unless you're using a modern computer, well, building a modern computer in Minecraft, which you're not going to do. I have yet to explain that yet, but it's just completely out there. But anyways, the computer that you're watching this on, though, is probably capable of doing square roots or something. But I'm getting off on a tangent. When building the ALU, you have to make sure that all of the functions that you intended to have in the instruction set are actually used. And so because of this, you're going to go back to the instruction set a lot and make sure that you've included all of them. So most computers almost always have add, subtract, move, and stop, just because it's stuff that you really need to have it in order for it to really be a computer. Now, if you're going to have some like more complicated stuff for your baseline, I'll probably also want to have conditional branching, but we're going to be getting to that at a later date. Anyways, so registers. The instruction set basically defines special things that the registers can do. And it basically tells you how many there are, and it can also tell you special things. For instance, in the original instruction set that I was going to have for this, we actually planned on having one of our registers be a program counter, but that was not going to work out very well, just because it would have been hard to get the information on a direct route to memory, but we're going to be talking about the program counter significantly more a bit later. Anyways, so the instruction set is, it can also specify if you have a regular computer or a stack machine, and a stack machine is basically where you don't have any registers, you just have a stack. There's other types of stuff that you can do with other types of memory, but yeah, we're going to be never covering stuff like that. I just thought I might as well mention it. Anyways, so speaking of memory, we can actually define in the instruction set some special things about it. For instance, how much it is, how you can access it, etc., etc., etc. And the way that you actually access it, we're going to be explaining this much more in depth later, but the way that you access it is by means of a pointer. And a pointer is basically when you use data from the register as the address in memory. If you remember from memory, if you have a whole bunch of RAM or ROM, then it's going to have addresses, which is basically where you can look up specific stuff. So the data that you have in your register is just then going to be plugged in as the address. It's sort of like you have your address in real life. you basically, if your CPU is the, let's just say the mail warehouse, then one of the things in the mail warehouse is going to be the address of your house as to where it's going to be mailed to. And so yeah, that's basically pointers. They're a bit confusing, but we're going to be basically discussing it a bit later. And so when you define a register in the bit layout, which we're going to talk about a bit later, each register has two modes. And one mode is where you just use the input, the data that's in that register, and you just send it straight into the ALU. Whereas you could also just take that information and you could use it as a pointer from memory. And the information that you get back out of memory is the thing that goes into the ALU. So yeah. Anyways, so the instruction set is also capable of defining other special things that you can have in your CPU, or rather the control unit, more or less, because it's the control unit's job and really the computer's job in general to execute the instruction set. And so, yeah, it basically defines stuff like the program counter and the CPU flags and a few other stuff if you want to do special stuff like single operanded instructions, but we're going to get to that a bit later. Once again, we need to discuss bit layout first. And bit layout is our subject now, and bit layout is probably the most complicated part of all of this, so bear with me. The bit layout, basically, it determines what an instruction means. And you might be confused at that, but basically, the way that each clock cycle works is that the program counter will first read out its information, and that will go to memory. Memory is going to look at what's at that address, and it's going to read the value that's at that address out, and it's going to send it to the control unit. The control unit then somehow decides what exactly that instruction means for the CPU to do, and then it can manipulate stuff within the data loop, depending on what exactly that instruction means. So yeah, that's basically what that is, and the bit layout basically tells you what the string of ones and zeros that comes out of memory into the control unit means. And yeah, so it's a bit difficult to wrap one's mind around, so we're going to go into Minecraft for just a second, because Minecraft's much more visual than what I can do here. So, how on earth is this number right here, which I'm representing with numbers, supposed to get into the CPU and define an instruction? And the answer to that is that we just actually split it up into three different parts. We're going to split it up into an opcode, register A, and a register B section. The register B is also going to have a mode B, and it's also going to, and register A is going to have the same thing. And so because of that, that's basically how we're going to split it up. And then one of these is going to be the least significant bit, and then the other one is going to be the most significant bit. So you might be wondering, what exactly does this mean? And the answer is that basically these two wires right here, we're going to go really far back. Remember states. Remember that these two wires right here have a total of 4 different states that they can be in. Both off, this one on, and both on. So about those 4 different states that we can be in, each one of those is going to correspond to a different function or opcode, and that's basically going to be what happens in the clock cycle during that, when that instruction goes in. Now for the registers, it just tells you the registers that are going to be used, and voila, you have the entire thing. And there's a bit more to this, which we're going to be discussing in just a second, but this is really all that we need to know. And this is actually the bit layout that we're going to be using in our CPU. So right here we have register A for 3 bits, and then one of them is a mode. And this, of course, if you remember, basically says that if this is off, then this is going to, what's it called? Then we're going to be using whatever the register that's defined by these 2 bits is pointing to, rather than what it actually is. And this is the B register. And there's something curious that we're going to talk about the B register in just a second, but yeah. So yeah, that's just about it, and we'll go back to PowerPoint. Alright, so now that we've finished that, we can move back to single operanded instructions. So yeah, so basically in our bit layout, it has two sets of bits that are defined for the register. One of them is for the A input and one is for the B input. Your A input is one input of your addition, and your B input is the other input of your addition. So if register 0 contained 3, and you were to say do register 0 plus register 1, and register 1 contained 2, then that would be 3 plus 2. But what happens if you want to do a really simple function, like incrementing, or branching, or stopping the program? And for those, you don't either need 1 or 0 registers to get the result. And so what we actually do is that we have one of our opcodes say, okay, we're actually going to have a different bit layout. We're going to have it so that these two bits in this always have to be 1, because in order for it to change to this format, it has to be like that. And then the ones that would be our extra register that we don't need because we're doing a simpler function are going to become our opcode. And this makes it so that we can have a total of 4 double operanded instructions, minus 1 because we have to have one of those functions be single operand instruction, and then you have 8 other instructions. So that, if you add it all up, makes a total of 11 functions rather than 4. And that's just really convenient for us, because otherwise it would make it so that we couldn't really do much with our instruction set, well, our bit layout, because it just wouldn't have allowed much space for us to really program anything. So yeah, and here's the remainder of our instruction set, finally, yay! So the functions that we have, as far as double operanded instructions go, we have add, subtract, move, and our single operanded instruction command. And as for the single operanded instructions, we have increment, decrement, left shift, right shift, branch unconditionally, branch carryout, branch underflow, and stop. Now for our registers, we just have 4 general purpose registers. For memory, we have 64 total bytes, 32 RAM, and 32 ROM. And other things, we just have a single operanded instruction format. And yeah, that's just about it. I hope you guys have enjoyed, and I will see you guys next time.